Hi, my name is Trevor Barcelo. I'm the Product Line Manager for Battery Charger Products at Linear Technology. Today, I'll talk about the LTC 4015 multi-chemistry battery charger with battery health and power system monitoring. Modern high-performance and high-reliability industrial, medical, and military applications demand a variety of battery chemistries with a wide range of battery pack voltages. Monitoring battery health and system performance is critical to ensure reliable and robust operation. To accommodate these applications, the LTC 4015 combines a state-of-the-art 35-volt step-down switching controller with a 14-bit analog-to-digital converter, or ADC, and Coulomb Counter. 9 different charge algorithms can be selected to charge lithium-ion, lithium iron phosphate, or lead-acid batteries. For lithium chemistries, the LTC 4015 can charge up to 9 series cells. The device can also charge 6-volt, 12-volt, and 24-volt lead-acid batteries. Keeping in mind it is a step-down controller, the LTC 4015's 35-volt maximum input voltage allows it to operate from many power supplies, including common 5-volt, 12-volt, and 24-volt sources. Furthermore, the LTC 4015 includes a full maximum power point tracking, or MPPT, algorithm that optimizes performance when charging a battery from a solar panel or other power-constrained source. The LTC 4015 is well suited for charge currents that range from 1 amp up to at least 12 amps. To help ensure that current goes where it should, and to prevent it from going where it should not, the LTC 4015 includes drivers for an input FET and an output or battery FET. These FETs function as an ideal diode OR between the input supply and the battery. This topology allows the application to draw power directly from the input supply when available and to completely disconnect the battery from the system when fully charged or during a temperature fault. To allow proper functionality from current-limited or power-limited supplies, the LTC 4015 implements an input current limit. If the combination of the system load and the battery charge currents reaches the input current limit, then the charge current is automatically reduced to prevent an input overload condition. The core function of the LTC 4015 is to charge batteries. Each of the internal charge algorithms controls constant current to better than 2% accuracy and constant voltage to better than 1% accuracy. Precision internal current sense amplifiers allow the use of a small 32 millivolt full-scale charge current sense voltage, which minimizes power dissipation without compromising charge current accuracy. As mentioned, 9 different charge algorithms are included for battery voltages up to 35 volts. 6 different tri-state inputs, 2 chem pins, and 3 cells pins are used to choose the proper settings. This slide shows how to program Chem 1 and Chem 0. Each of the 3 chemistries has at least one fixed, non-programmable algorithm, as well as one programmable algorithm. The fixed algorithms are intended for designs that do not allow software control of any facet of the battery charging process. However, even the programmable algorithms are designed to rely on hardware checks to prevent software from causing battery safety issues. The hardwired chem and cells pins ensure that the LTC 4015 recognizes the type of battery it is charging, as well as how many battery cells it is charging. With this information, the device ensures that the charge algorithms never apply a voltage or current to a battery that would cause a safety concern. The programmable algorithms include the ability to adjust several charge parameters, including charge voltage, current, or time termination, and temperature qualification parameters. An example of this programmability can be seen in the optional JETA temperature profile. 7 distinct temperature regions are programmed by 6 set points. In 5 of the regions, independent charge voltage and charge current values can be programmed. The outer 2, too hot and too cold, do not allow any charging. The JETA charge profile shown here can be used as is or adjusted as needed. For lead-acid batteries, a negative temperature coefficient is applied to the charge voltage. With this degree of programmability, a wide range of temperature charge profiles can be used to ensure a safe charging environment for all batteries. In order to adjust the temperature set points, it is necessary to communicate with the LTC4015 using its I2C serial port. In addition to being able to adjust charge parameters, this same serial port is used to read information from the Coulomb counter, monitor system parameters, program parameter limits for the alert system, and read status information. Most of the information available comes from two dedicated pieces of internal hardware, a precision Coulomb counter and a 14-bit ADC. The Coulomb counter obtains battery state of charge information by monitoring the time integral of battery current. Because an independent continuous time precision integrator is used for the Coulomb counter, it never misses dynamic battery current signals and provides exceptional precision over a wide dynamic range. An adjustable prescaler allows matching of the 16-bit Coulomb counter value to the battery capacity of interest. The Coulomb counter functionality has built-in high and low limits, which can be used by the alert system. So what is this alert system? It provides users the ability to monitor only the system parameters of interest. While the Coulomb counter provides the battery state of charge information, the 14-bit ADC provides data from several other parameters, including battery voltage, battery current, both charge and discharge, battery series resistance, input voltage, input current, system voltage, die temperature, and thermistor voltage to monitor battery temperature. Furthermore, charger status bits are available to indicate which phase of the charge algorithm is being executed and whether or not a battery is present. The battery series resistance parameter is of particular importance because when combined with the Coulomb counter information, the overall health of the battery can be tracked. Battery series resistance tends to increase as a battery ages and degrades. By setting a limit on this resistance, the system can be alerted and the user can be notified to replace the battery prior to a catastrophic failure. Most of the system parameters have both high and low limits, which can each be programmed. Finally, a programmable mask register can enable or disable each of the system alerts. For example, the LTC4015 can be programmed to set an alert if the input voltage falls below 11.5 volts or the lead-acid battery algorithm enters the absorb phase. Now let's look at some real-world examples using our LTC4015 demo board, DC2039A, and its GUI. The default demo board configuration here is set to charge a stack of 2 lithium-ion batteries as shown in the upper right corner of the GUI. The input, battery, and system voltages can be read across the top of the screen, while the dial gauges show the input and battery currents. Let's start by launching the Coulomb counter configuration wizard. By choosing a battery capacity of 1,333 mAh, the Coulomb counter increments 10% every minute due to the 8 amp charge current. We'll let that run while we examine some other features. As previously described, the limits and alert functionality enables a user to monitor many parameters. Let's set a battery series resistance, or BSR, high alert limit of 120 milliohms. Going back to the GUI configuration tab, I can take a BSR snapshot. It currently reads 95 milliohms. With my 50-watt rheostat, I can increase the series resistance by approximately 100 milliohms and take another BSR snapshot. The measured value increased to 205 milliohms, and an SMB alert showing that the BSR resistance limit is exceeded is set. I can reduce the series resistance, take a BSR measurement, and clear the alert. Now let's check back on the Coulomb counter. The stopwatch indicates that about 45 seconds have passed, and you can see that the Coulomb count has increased from its initial value of 0% to about 7 or 8%. Perfect. The Jada curve page allows the user to adjust the temperature set points as well as the charge current and charge voltage in each temperature range. The DC2039A demo board includes a digitally controlled resistor to simulate ambient temperature changes. Next to the simulated NTC temperature is a readout of the LTC4015 die temperature as measured by its on-chip temperature system. The GUI highlights many of the LTC4015 features and gives you a good idea of everything that can be measured and monitored. The LTC4015 is an exciting new IC that can charge a wide variety of batteries while simultaneously monitoring battery health and overall power system performance. Standalone operation makes the LTC4015 well suited for systems with or without a host microcontroller. The LTC4015 is a key component in a robust, high-reliability battery-powered system. Please visit linear.com for more information. Thank you for watching.